We are now going to talk about two of the most interesting weather phenomena that are out there, tornadoes and hurricanes. Let's start with tornadoes. What exactly is a tornado? Well, it's a violent windstorm, we know that. It's an extremely low pressure center. It's often associated with severe thunderstorms. Remember from the last video that thunderstorms are produced at the leading edge of cold fronts. So here we have a cold air mass moving into warm air. That's the definition of a cold front. And so warm air is being pushed up, forming cumulonimbus clouds. And if this is an intense precipitation event, we might get a tornado. Tornadoes have the steepest pressure gradient of all low pressure systems. Now, what exactly does that mean? Let's take a look at some of the different kinds of low pressure systems that there are. First of all, we've already looked at mid-latitude cyclones, which are low pressure systems. And here's a picture from lab. Remember that this particular kind of low pressure system is very common in weather systems across the mid-latitudes. Here's the low pressure center, and here are the isobars listed every 4 millibars around that system. If we compare it to a hurricane, where we also have isobars listed every 4 millibars, we can see that this hurricane has the isobars much closer together. Now, we haven't looked at hurricanes yet, we will later on in this video. You can see that these isobars are much more tightly spaced around the low. The low in this picture would be right in the middle of this hurricane here. And they're much more tightly spaced than over here. So the gradient of the hurricane is much steeper than the gradient over here. But if we move on to tornadoes, it's even more tightly spaced. It's hard to see the map over here, but I've highlighted the lower peninsula of Michigan in this picture, so you can kind of try to see where you are. These isobars are not every 4 millibars, but every 1 millibar, so there's a lot more of them. But still, I think you can see this extremely tight grouping of isobars right here. So that's what the pressure gradient means. They're very, very tightly grouped, and that means the pressure changes very, very quickly as you get close to that tornado. What's going on inside a tornado? Well, we really don't have a good idea for that because you can't set up an instrument and measure a tornado the same way you can a hurricane. Hurricanes are big, they're around for a long time, we can even fly airplanes into them. Tornadoes are temporary events, and to set up an instrument and hope that a tornado will pass over it, that's a pretty big long shot. And also the speeds of wind in tornadoes are much faster than hurricanes in some cases, and your instrument will probably be blown away. So we have to do a lot of computer modeling. And what people think is happening inside the tornado, so this is the entire tornado spinning counterclockwise, and within it are these vortices of additional uprising air that are themselves moving counterclockwise around the tornado. Then we have this entire system moving in one direction. That would be the path of the tornado moving with the storm. How do these form in the first place? Again, something that's still trying to be understood. One idea is that because there's so much wind involved in this situation, you get sort of a rolling pattern of winds because there's stronger winds at the top compared to the weaker winds along the ground surface. The rising of air that's going on around this whole region then pushes that rolling region of wind upwards, somehow incorporates it into the big cumulonimbus clouds that are forming, and that spawns the tornado. Remember, everything is rising in this particular situation. Even the air in the tornado is rising. We think of tornadoes as touching down, but they are intense rising air regions. Notice in all the pictures you'll see, the tornado is always coming from a large bank of clouds above it. It's never just coming out of a clear sky or just a little tiny cloud. It's always coming out of some huge mass of clouds. For example, here's a tornado coming out of this entire gigantic cumulonimbus cloud system. Here are some more examples. Now, this region in the country right here is sometimes called Tornado Alley because this is where we most frequently see tornadoes. Let's take a look at why that is. Here are some more data that show why this area is called Tornado Alley. This is showing the number of annual tornadoes, and this region right here is where we have 7 to 9 tornadoes a year on average. Most of the rest of the country has less. Florida is close with about 7 in some areas. This region right here is where we have our mid-latitude cyclones passing with those cold fronts every year. So this region tends to experience the most tornadoes. Here's an example of a path that a tornado made as it passed through an area in Wisconsin. This occurred in 2007, and this path ran for 40 miles. It never got wider than 1 kilometer in its width. And this is what I mean when I say setting up an instrument to try to catch information. If you put your instrument even just over here in hope that a tornado would pass over it, you would have missed it. And if you put it right in the path, it probably would have been wiped out. If you're unlucky enough to be in the path of a tornado, however, the winds are extremely strong, even strong enough to blow metal into a wooden structure such as this here. There is a scale for tornado strength, and in many cases these wind speeds have to be estimated based on the damage. So here's some damage here. It's called the Fujita intensity scale, and it's a scale of 0 to 5. And what's interesting is that there's also a hurricane scale. I'm sure you've heard of Category 1, Category 2 hurricanes. The highest, fastest, most damaging hurricane is at Category 5, and the winds in a hurricane Category 5 are about 250 kilometers an hour. So you can see that there are tornadoes that have much faster winds than hurricanes. And so they're smaller scale, but they can be much more damaging in terms of their wind speed. So let's move on to hurricanes. Hurricanes are the greatest storms on Earth. They're the lowest air pressure on Earth, and they need to form over warm water. So here's a picture showing water temperatures in the Atlantic, and 27.8 degrees is showing the yellow color, and that's about 80 degrees Fahrenheit. You might not think that the ocean water ever gets that warm, but it does in the summer. And everything that's more of an orange or red color is warmer still. So these are all regions where hurricanes can form. They also have a limited region of where they can occur. They need to occur between latitudes 5 degrees and 20 degrees north or south of the equator. And that is shown in this picture. Everything in red is showing where hurricanes occur. They don't occur near the equator because the Coriolis effect is very weak at the equator. And hurricanes need that spinning motion. They need that rotation that the Coriolis effect provides to build stronger and stronger. So they form at least 5 degrees away from the equator where the Coriolis effect can play a role in their development. One of the key things I want you to remember about hurricane formation is the energy from hurricanes comes from the condensation of water vapor. Taking another look at that figure I just showed you, I just want to point out that hurricanes aren't called hurricanes everywhere. They're called hurricanes in the Atlantic Ocean, but they're called typhoons in the Western Pacific Ocean and cyclones in the Indian Ocean. These are all the exact same storms. They just have different names because they were named before the whole world was talking to each other about these storms, and those names have stuck. Hurricanes are defined on the basis of their wind speed. Before something becomes a hurricane, when the winds aren't that strong, they are identified as either a tropical depression or a tropical storm. A tropical depression is something that is less than 38 miles an hour, but it's maybe close, and so meteorologists keep an eye on it. A tropical storm has winds between 38 and 74 miles an hour, and this is when it is given a name, like Tropical Storm Dennis. After that, once it goes past 74 miles an hour, it becomes a hurricane, and it has a category 1 to 5 depending on its speed. Here's the scale, the Saffir-Simpson hurricane scale, with the category and the pressure in the middle, which you'll notice is lower and lower and lower depending on the category. The wind speeds increase. The storm surge increases. And so the storm surge is something I'm going to talk about in a minute, but this is how much water is pushed on shore when the hurricane arrives. And then the damage, of course, increases the greater the number of the category. This is showing the hurricane scale again, but in an interesting format. This is sometimes called a spaghetti diagram. And what it's showing with the colors is the average level of wind speed or intensity of hurricanes as they move along their paths. So for example, in the Atlantic Ocean, a hurricane would start out as a tropical depression and become a tropical storm, and then build up to a 1, 2, 3, maybe a 4 or 5, and then usually they turn and go back out and diminish in their wind speed. you can see quite readily that the worst storms seem to be the typhoons over here in the Pacific. And that's because the Pacific Ocean is larger than any other ocean. And the more one of these storms spends over the water, the more it builds up its energy and its strength. Let's talk about the different parts of the hurricane. You're probably familiar that there's an eye in a hurricane, this central round part that is generally free of clouds. That's called the eye. And then around the eye is what's called the eye wall. It's the part that surrounds the eye, and it is the most intense part of the storm. The eye wall is this ring of towering cumulonimbus clouds, and you can see this little cutaway view. It's where the air rises at the center of the hurricane, and it's got the greatest wind speeds and the heaviest rainfall. The eye, on the other hand, at the center of the hurricane, is the calmest part of the storm, and it can be as much as 20 kilometers in diameter. It has descending air, because all that air going up has to eventually go somewhere. It goes down, and it's actually warm. It's compressed air because it's sinking, and it's the warmest part of the storm. Precipitation and wind actually stop. So if the eye of a storm goes over you, everything kind of stops. But if the eye goes over you, you know the other side of the eye wall is coming soon, so it's not really necessarily a good thing. You've probably heard the expression of being in the eye of the storm. That means the worst is yet to come. I wonder if you've ever seen this movie called The Day After Tomorrow. It's about these super giant storms that come over Earth and freeze the whole Earth. Well, there's a lot of scientific inaccuracies in that movie, and one of my favorite is when one of the characters is in a hurricane, one of these Earth-size hurricanes, which can't happen for a number of reasons, but the eye of the storm appears and the character freezes to death. Well, as I've just mentioned, the eye is supposed to be the warmest part of the storm, so Hollywood got it wrong. Okay, we're going to have to continue hurricanes in the next video, part 2.